1927, Albert Einstein boarded a train to Solvay in Belgium. His journey would take him to the center of an argument between the greatest collection of scientists assembled this century. By the end of this conference, Einstein had lost a battle, and our understanding of the world had changed forever.
Quantum mechanics, in a nutshell, is the physics of the very small. Anything as small as an atom or smaller than that works in accordance with the rules of quantum physics.
And it's a very surprising discovery that the physical world at that scale is totally different in its behavior and character from the physical world of every day that we experience directly. The everyday world is clear and reliable. The quantum world, it turns out, is cloudy and fitful. So that was a big surprise.
Quantum physics has revolutionized our understanding of the world. The journey to the mysterious heart of the atom has forced scientists to take sides in a debate about the uncertain nature of matter, a debate that still continues today. It all began in 1897 when J.J. Thomson discovered that electricity was caused by the flow of tiny particles called electrons.
What Thomson decided was that he had found a subatomic particle which is a constituent of all matter.
And why is that important? Well, our entire understanding of matter today, normal, ordinary, garden variety matter, why grass is green, why the sky is blue, that understanding is based on how electrons interact inside of atoms.
Although Thomson and his colleagues understood the scientific importance of the electron, they didn't see any practical use for it.
Could anything at first sight seem more impractical than a body which is so small that its mass is an insignificant fraction of the mass of an atom of hydrogen?
They in fact had a toast at one of their annual dinners, which was, to the electron, may it be of no use whatsoever. Now, that's obviously very ironic because the understanding of the electron has led on to tremendous practical applications.
This pulling of electrons from atoms isn't done for amusement.
The electron particle was to make its first commercial impact in the cutthroat world of the American telephone industry. In 1907, the telephone was already 31 years old. AT&T, the company founded by Alexander Graham Bell, was facing stiff competition from thousands of smaller companies. The race was on to be the first operator to provide a long-distance service between the east and west coast of America.
The technology to do that didn't exist.
Can you recall the telephone of a generation ago? New York to Denver was the longest call that could be made.
The major technological problem that stood in the way of completing a long-distance line was amplification. As an electrical signal travels down a copper wire, it weakens. There's resistance in the copper wire. Eventually, it weakens to the point where there's no longer a usable signal. They needed a way to amplify the signal.
Desperate for a solution, AT&T invited anyone with an idea to contact them.
One person who did was an independent inventor named Lee DeForest. DeForest in 1906 had invented something called the Audion, the first three-element vacuum tube. He was using it primarily as a detector of radio waves, but he knew also that his device would provide a small amount of amplification.
But not nearly enough for AT&T. The Audion amplified the telephone signal by altering the flow of electricity between a metal plate and a wire surrounded by a vacuum. The problem was there was only a partial vacuum inside the Audion.
The space between the wire and plate is jam-packed with gyrating air atoms. And to reach the plate, the electrons would have to bump their way through them like midgets in a subway crowd.
The solution was to pump out more air. By doing this, the first useful electrical amplifier was born. AT&T used these high vacuum tubes to complete the transcontinental telephone line in 1914.
How much is your voice amplified by these repeater stations between New York and San Francisco? You say it. I can't. The figure is 10, with 99 zeros after it.
It was only made possible because of J.J. Thomson's earlier discovery that electricity was the flow of tiny particles, electrons. Theoretical physics had a commercial value after all. A lesson not lost on AT&T.
The transcontinental telephone line was an important step in knitting the nation together. The other effect it had was to firmly convince leadership at AT&T that bringing science in-house, hiring scientists, engaging them in doing research, was something that was a good business strategy.
They set up the Bell Telephone Laboratory. The high vacuum tube, or valve, became the workhorse of a new communications industry. Commercial radio and later television were made possible by the valve amplifier.
Yes, sir. If it weren't for these babies, there wouldn't be any radio.
At the same time, scientists were wrestling with radical new ideas about how electrons behaved.
At the end of the 19th century, it looked as though, essentially, we knew how the physical world behaved. There were the triumphs of Newton, which described how particles behaved, and gave you means of calculating what they would do. And then in the 19th century itself, the great achievement was Clerk Maxwell's theory of electromagnetism. That showed that light was a wave-like thing, waves of electromagnetic energy. And really these issues seemed to be settled, and many great physicists thought all that was left was just to tidy up the details, to dot the I's and cross the T's.
In the Victorian era, it seemed everything in the physical world was either a lumpy particle, like an electron, or a spread-out wave, like light. But in 1900, German physicist Max Planck saw there was a big problem with the wave theory of light. Planck was looking at the way light and heat radiates from hot bodies, like a furnace. Everything known about physics said that the radiation should behave like a smooth, continuous flow, a wave. But the calculations done with the wave theory didn't match observation.
Planck began to think about it, and he saw that you could get round this. The calculations were wrong because they were assuming that the radiation was behaving just like smooth flow, like the flow of water from a tap. He saw that, in fact, the radiation was not behaving that way. It was coming in drips, as you might say, in packets, one at a time. One packet of energy followed by another packet of energy. These packets consisted of so much energy, and so it was a quantum of energy, so much of energy, and that's where the name quantum and quantum theory comes from.
Planck's quantum theory suggested the seemingly impossible. Light could be both a wave and a particle. It was so impossible that Planck stopped short of saying so.
He found that you could only explain the way light comes out of atoms, the spectrum of light, in terms of little packets of energy coming out. But he never suggested that the light only existed as little packets of energy. And the analogy I like to use is with a cash dispenser at a bank. If you go to the cash dispenser at my bank, you can get money out in multiples of £5, but there's no way you can get £4 out because it can't give you coins, it can only give you notes.
The leap of imagination came from a young patent clerk who in 1905 dared to think the unthinkable.
Einstein said, it's the light itself that only exists in lumps of a certain size.
Einstein reinforced the concept that light had a particle character. The whole of 19th century physics has shown that it had a wave-like character, so the physicists of the day were left with this intolerable paradox, really, that sometimes light looked like waves, sometimes like particles. And I think it's fair to say that most of them were so upset by this, they swept it under the carpet and said, we won't bother about that. But of course, some people persisted, and through their persistence, modern quantum theory eventually was discovered.
The revolution in physics would have to wait for more urgent matters to be resolved. By the end of the Great War, a new generation was now ready to question the established order. Physics was no exception. The catalyst for change was a young French aristocrat, Prince Louis de Broglie.
Louis de Broglie was a young student in Paris, and he said, okay, light has been found to have this funny behavior. We thought it was waves, but it turns out sometimes it's also particles. Now, there are lots of things around which we've always thought of as being particles, things like electrons and so on. maybe they sometimes behave like waves. Maybe what's sauce for the goose is sauce for the gander.
We think we understand particles. We think we know what things like billiard balls are. And when you say no, you have to think of these things as being wavy as well as being particle-like. You have to apply quantum rules to electrons. That was a really big step.
De Broglie came up with the remarkable idea that everything is a little bit wavy while he was still a student. The theory gave his tutors something of a headache.
De Broglie's examiners at the university were reluctant to give him a degree for such a fool idea. He got the degree all right, but only because Albert Einstein happened to be visiting Paris at the time and said, look, this isn't such a bad idea. Maybe it's even true.
Although Einstein championed the idea of wavy electrons, there was no experimental proof. In fact, quite the opposite. J.J. Thomson had got the Nobel Prize for proving it was a particle. But eventually, confirmation of the wavy nature of electrons did come.
The key experiments in the 1920s that proved that electrons are waves did so by firing electrons at the regular structure of a crystal, rather like the latticework structure we've got here. And those experiments showed the electrons bending round the atoms in the crystal, just as the waves here are bending round the structure of the pier. George Thomson in the 1920s was involved in experiments that showed electrons behaving as waves, doing just the things that ripples on a pond do, being diffracted, interfering with one another, all those kinds of things. And the story culminates because J.J. Thomson, the father, got the Nobel Prize for proving that electrons are particles, and George Thomson, the son, got the Nobel Prize for proving that electrons are waves. And they're both right. That's really the core of quantum physics summed up in that. Both of those Nobel Prizes were deserved.
It was the best of times and the worst of times for the physicists. They were in the middle of a revolution. They were struggling to come to terms with a problem that still troubles scientists now. Is the electron a particle or a wave? Or both?
If you asked, so to speak, if you asked light a wave-like question, lo and behold, it gave you a wave-like answer. But if you asked it a particle-like question, it gave you a particle-like answer. It conformed to what you asked it to do. In that sense, there wasn't a direct contradiction. There was obviously a very deep puzzle about how such behavior was possible, but at least there wasn't a flat-on collision. It wasn't at the same time behaving like a bullet and like a spread-out flappy thing.
It's kind of like putting on two different sets of glasses and seeing the world in two different ways and being able to flip-flop back and forth between those two pictures. The general public doesn't have that ability, so they really see it as a very weird Alice in Wonderland world, and it disturbs them. Frankly, although I may seem very calm, it still disturbs me a bit too.
The disturbing nature of the electron confounded scientists in the 1920s. The Austrian Erwin Schrödinger set himself the task of writing down an equation that would predict how the wavy electron would behave. In 1926, he succeeded.
And in fact, it's a very simple equation. I could write it down on the back of an envelope with a great deal to spare. And here, in fact, it is. It simply has two terms in it. On one side of the equation is how things change with time. And on the other side of the equation, it says that's related to the energy of the system, which is the fundamental way of describing things in quantum mechanics. So there it is, a very simple equation. And the whole of atomic and subatomic physics, in some sense, flows from that equation. That shows you something of the wonderful power of mathematics to condense and crystallize out physical truth.
Although the behavior of the wavy electron could now be calculated, what no one could predict was that the wavy nature of matter was about to cause a major split between the quantum pioneers. If electrons were particles, it would be possible to know exactly where they were and how they would move around. Isaac Newton's laws of motion, written down in the 17th century, described precisely how particles of any size, from an apple to the moon, behaved. The certainty of Newton's world made the Industrial Revolution possible. The motion of anything could be predicted. The most intricate machines could be built. They ran as reliably as clockwork, just as Newton imagined the whole universe to work. It seemed unquestionable that nature was utterly predictable.
Newton's equations tell you exactly what's going to happen in the future. It turned out that the quantum world, the small-scale world, is different from that. It's unpicturable to us. It's cloudy in its character. And it's probabilistic, meaning that we can't say for certain what's going to happen. If this may happen, that may happen. We can say what the chances are, but that's as far as we can go.
The man who first realized the world runs on quantum chance was Werner Heisenberg. In 1927, he proposed the uncertainty principle. It states that because matter is spread out in space, wavy, it's impossible to say exactly where it is and what it might do next simultaneously.
This is absolutely real down in the depths of quantum physics. An electron itself does not know where it is and where it's going.
So we can never be certain about what's happening inside an atom. The effects are so small in our everyday world, we never see them. But the fact that at its heart, nature is a game of chance, meant scientists had to concede there was a real limit to what they could know with certainty. For many, this was unacceptable.
Several of the quantum pioneers didn't like what they'd invented. Max Planck wasn't really happy with it. Einstein wasn't happy with it. Schrödinger wasn't happy with it. And Einstein hated the idea that the outcomes of experiments could not be completely predictable. And in the famous expression, it's usually quoted, he said that I cannot believe that God plays dice with the universe.
And he thought that meant that the physical world had to be absolutely objective, had to be absolutely determinate and clear and certain. And of course quantum mechanics wasn't like that, and so he came to hate his grandchild.
From across Europe, the greatest minds of the age came together to settle the matter of uncertainty. The place was Solvay in Belgium. The year was 1927. The single photograph that remains of the conference shows a unique collection of scientific genius. Max Planck is next to Marie Curie. Behind Einstein are the other great doubters of uncertainty, like Prince Louis de Broglie, the original proposer of the wave theory. And on the top row, Erwin Schrödinger, whose equation made mathematical sense of wavy matter. Schrödinger and the others were not willing to take the leap into uncertainty with the Young Turks Pauli and Heisenberg.
They've said, we've got to go with the new physics, that's the way the world is, you can't quarrel with that. And there's some quite sharp arguments and discussions between Einstein and Bohr on the one hand, and between people like de Broglie and a very sharp-tongued Swiss physicist Wolfgang Pauli, who essentially told de Broglie, I think, to shut up. He was being stupid. And de Broglie was a sensitive person and didn't like that, and he actually went away and did shut up. So it was a sort of turning point moment in which the Young Turks won out over the old God.
He couldn't believe that the outcome of an experiment depended on chance. And that's what led Einstein, for the last 20 years or more of his life, to fight this more or less lone battle against the theory that was taking physics by storm and try to find flaws in it. And he kept trying to invent experiments, thought experiments, imaginary experiments that would prove that quantum physics couldn't be true. And every time he did, people found ways round his thought experiments and found that they didn't prove that at all. And ultimately, perhaps just as well for him, after he'd died, people actually did some of these experiments for real, and every time they found quantum physics is right, probability rules.
By the late 1930s, quantum theory had found a new home, as European scientists sought sanctuary from Nazi oppression.
So there was this huge shift of science to America. You have this rich country and you have this ability to apply massive technology and money to fundamental problems.
But Americans, by and large, have taken quantum mechanics as a very useful tool and said, oh, don't bother me with all these philosophical arguments. I just want to be able to make calculations. And that's where our strength is, that we have taken this pragmatic viewpoint and ignored what are some troubling aspects. If we really sat down and thought about the philosophical meaning of what we were working with, we might not get anything done.
The company that had already made a fortune from knowing the electron was a particle were by now exploring the commercial potential of the wave theory of electrons.
Bell Laboratories began a research program in the 1930s to investigate possible solid-state physics alternatives to the vacuum tube.
Of course, we cannot build a calculating machine as flexible as the human brain. But even a man-made computer, designed to do hundreds of brain-like calculating jobs, might need an Empire State Building to house it and a Niagara Falls to power and cool it, if vacuum tubes were used in its construction.
Vacuum tubes were power hungry. Vacuum tubes gave off a lot of heat, which had to be handled. Vacuum tubes wore out and had to be replaced.
The goal was to replace the unreliable glass vacuum tubes with tiny solid devices that didn't need a vacuum to work. Scientists already had a good idea of how electrons moved inside a vacuum. They behaved like particles.
These aroused monkeys throwing pebbles at a target through a shutter ably portray what goes on in a vacuum tube.
But inside a solid, a crystal, the electrons behaved like waves, spreading out and bending around the atoms. To make electrons work in a solid, you need to know about quantum mechanics.
And because electrons are not only particles but also waves, and waves are spread out, then the electron wave sample the overall structure of the crystal, just as the particle-like aspect of electrons carries the unit of electric charge. So in a curious way, the particle-wave duality of electrons is essential, both aspects of it are essential for understanding how electrons behave in solids, and therefore how electronics works.
In the early 1930s, solid materials were already being used in electrical circuits to detect radio waves. These solids were called semiconductors because they conduct just a little bit of electricity. Using quantum theory, for the first time, scientists could control the flow of electricity with precision. In the 1940s, this led to the development of semiconductor technology as a vital war weapon. Semiconductor radar could detect very small features like the conning tower of a submarine. It was this technology that Bell Labs used just after the war to create the modern era of electronics. The transistor was the semiconductor device that could amplify electrical signals, just like the vacuum tube, only better. The tiny transistor was the result of over 10 years' hard work at Bell Labs applying quantum theory to solve a practical problem.
The head of the department was William Shockley. The two key players in the transistor story, along with Shockley, are John Bardeen, a theoretical physicist, and Walter Brattain, an experimental physicist. On December 16th of 1947, they succeeded for the first time in amplifying an electrical signal with a solid-state device. A few days later, on December 23rd, they demonstrated their device to the department head Shockley and to a group of other Bell Labs scientists, and the transistor was born. But it was a lot of hard work, a lot of brilliance on the part of the scientists involved. It was not, oh, what are you going to do at the office today? Oh dear, I'm going to go to the office and invent a transistor. It's a lot harder than that.
The payoff was enormous.
Through their efforts, you may be able to get music with a flick of your wrist from the so-called Dick Tracy radio.
The miniaturization made possible by semiconductors laid the foundation for a new electronics industry. The first transistor took over 10 years to make. Today, 10,000 times more transistors than the population of the Earth are made every day. They're shrunk down to act as the pumps and valves that drive electrons around microchips. It all depends on quantum mechanics and the strange wave-particle nature of the electron. Over 100 years after its discovery, we can actually see what an electron might look like by using the computer technology it created.
One of the neatest pictures that sums up the quantum world is the one where a ring of atoms has been made as a little fence. You can see the waves of what used to be thought of as quantum particles sort of filling this quantum corral, as it's called. They can't escape. They're stuck inside there, and the waviness is kind of frozen there and can be photographed. That's something that the quantum pioneers would have loved to see.
Schrodinger would have said, way cool, dude.
Don Eigler at IBM has used a quantum microscope to make pictures of atomic surfaces. Each step in this picture of a surface is just one atom high. On top of the atoms, the wavy pattern is caused by a sea of electrons.
These are just electrons which are trapped in the surface layer, but within the surface layer they're free to move around. These electrons are waves. And the waves, when they move, they sometimes bang into features on our surface, like the step edges or the individual atoms which might be sticking out of the surface. And when a wave bangs into something, it reflects off of that thing. And when you have a reflected wave adding together with the incoming part of the wave, it sets up what we call a standing wave. These are regions where there are large oscillations which are fixed where they are in space, and regions where the oscillations go to zero.
I've always felt that the wave function was just a description of a reality. And the reality was deeper. It was a particle. And the wave function was just something mathematical up in a physicist's head. To actually see a physical wave function rippling across the surface is rather disturbing. If I was really honest, I'd probably have to tell you that I need to go back and reassess the way I've pictured the world.
Well, I'm probably somewhere in error, or maybe I'm just a heretic. I don't believe in this wave-particle duality mumbo-jumbo. I think it's mostly just the leftover baggage of having started off understanding the world in terms of particles and then being forced because of the quantum revolution to think of the world in terms of waves, and we're stuck with this dualistic way of looking at these very small particles. Don't even think about them as particles. Electrons are waves. And if you think of them in terms of waves, you will always end up with the right answer. Always.
The great debate on the nature of the electron and the meaning of the quantum world lingers on today. The success of quantum theory is unquestionable, but its meaning remains for each one of us to understand on our own terms.
People sometimes say that quantum mechanics shows that God plays dice. I don't think that's the right way of thinking about it. What I think we should say about it is that the universe is not God's puppet theatre. It isn't under tight divine control. It is allowed in some sense to be itself and to explore itself. And perhaps the openness of quantum theory, the unpredictability of quantum theory, is at the level of atoms and lower, an expression of an openness which I think is in the universe all over.
People have a kind of a deep religious need to know truth about the universe, to know how the universe works. That's why they're fascinated by black holes. And quantum mechanics is the most mysterious and exciting part of physics, and so it touches that chord. So it's not just the physics, it's this sort of mystic experience of knowing about ultimate truth. I think that's the appeal.
Next week in Quantum Leaps, the hard facts about extinction.
Extinction is an inevitable fate of all species. And that we simply have to accept, because that's what the history of life on Earth tells us.
You can stay with the Open University's World of Science by visiting our Quantum Leaps website, or for an information pack about
are the valleys and peaks that belong to the world of atomic surfaces.
I really enjoy having the opportunity to work in two worlds, in the world that you and I normally work in and think about, the world of macroscopic objects, and then this other world, the very small world of atoms. But it's a long ways down there. It's very far to get from the world that we know about, the world of macroscopic things, things that we can feel and touch and see, to the world of atoms.
Just how deeply we can probe into the heart of matter has made startling advances in the last 100 years. New techniques now enable scientists to investigate remarkable new worlds.
This technology is not like walking down a forest lane or in a town. Nothing is familiar here unless it's been studied and studied and studied and proven many times over by different people. A lot of it is unknown. These things are of enormous curiosity to a scientist. It's almost the definition of a true scientist. I think it's the bottom line. Curiosity is what drives people to go investigate.
New imaging techniques invented at the beginning of the century have also meant that the complex chemicals of life have begun to reveal their secrets. The proteins and DNA which are essential to life, and the drugs like penicillin which fight disease.
It attacked the germs and the mice were cured.
These insights into the building blocks of life have revolutionized biology and helped make modern medicine. To bring us this new knowledge, the scientists have struggled to invent ingenious new tools, a journey that would take them far beyond the familiar microscope.
This is a Powell and Leyland microscope, which was made in 1864 and probably represents the peak of microscope manufacture in this country. One can see the solidity of the brass construction, the beauty of the sheer engineering.
At the end of the 19th century, the optical or light microscope was at the peak of its powers, a plaything of the rich amateur as well as a tool of serious science. It was helping to reveal the secrets of nature as well as its remarkable beauty. The first microscopes had been built in the late 1600s, often by wealthy enthusiasts in their spare time.
One of the most famous was a linen draper of Holland, an amateur, a gentleman, and he made over 500 simple microscopes. And we have a replica of one here. Only 9 of these genuine instruments still exist. As you can see, it's made of brass, rather crudely made, 2 plates which are riveted together. The lens is sandwiched between them and is located at that point. The specimen was impaled upon the point of the pin, and if one wanted to study the specimen, one had to hold the microscope very, very close to one's eye in this sort of fashion and point up towards a window.
At the same time as Leeuwenhoek was working in Holland, Englishman Robert Hooke had the idea of using 2 lenses rather than 1. The convenience of this design helped Hooke to pursue his new hobby.
This is Hooke's micrographia, and beautiful etchings here. He's made a very careful choice of what's shown to us in the arrangement. It's the beginnings of real observation. And it's also good art. I think this is the real spiritual value of science here. This is why we keep on doing things. We're curious, but also we want to see the beauty in it.
But the light microscope wouldn't be the tool to take 20th century science deeper into this hidden world, however ornate the design or exquisite the engineering. By the end of the 19th century, new understandings in physics were forcing the manufacturers to admit that they'd reached a dead end. The microscope and the human eye use visible light to image. But the wavelength of light is simply too large to reveal really tiny detail. The whole world of unknown atomic structure seemed to be beyond the scientists' reach.
It's interesting to look at this picture in detail. I can go up close and I can see the brush strokes, but there's a bit of a barrier. I can't penetrate through to the molecules of the pigment that is, I know, behind the brush strokes. Penetrating that barrier, that middle ground which we need to somehow negotiate as scientists dealing with the materials, that's actually the hardest thing to do.
As I'm going to speak to you for a few minutes on a subject which is perhaps a little abstruse, I must try and first
But
of
at
all
the turn of the century, a dramatic discovery was about to plunge scientists into the atomic world. The pioneer of this remarkable new way of looking into matter was the physicist William Bragg.
Not even the finest microscope that ever was made will bring us anywhere near seeing the atoms and molecules. But in the X-rays, we've got a new sort of light. A light which is something like 10,000 times as fine, as delicate as ordinary light. And here's our new chance.
William Bragg and his son Lawrence developed a technique which is today a cornerstone of investigative science: X-ray crystallography. Its discovery had a dramatic impact on all the sciences, from the structure of rocks to human biology.
I think X-ray crystallography has been the single most important structural tool that has revealed the microscopic world to chemists in this century. It wasn't just routine work. These people were really the pioneers.
The Braggs inspired a new generation of crystallographers whose work would transform our understanding and control of nature. British scientist Dorothy Hodgkin began her Nobel Prize-winning career thanks to William Bragg.
When she was in her mid-teens, her mother gave her a copy of a book, this book, called Concerning the Nature of Things by Sir William Bragg. And in that, he talked about X-rays and how you could use them actually to look into crystals of different chemicals and see the atoms. And Dorothy was fascinated by that, and that's what got her started. Let me read you just a little bit of it. He says, "But first let us realize that in the last 25 years or so, we've been given, so to speak, new eyes. The new knowledge, like all sudden revelations of the truth, lights up the ground over which we've been traveling and makes easy things that were difficult before." And I think she just saw those words as so inspirational, and this notion that you were going to be able to see atoms in crystals, she found tremendously exciting.
Bragg's new eyes were inspirational for another young crystallographer who would also win the Nobel Prize for his efforts. In the 1930s, Max Perutz started a marathon project to determine the structure of hemoglobin, the complex protein responsible for carrying oxygen around the body.
The structure of protein was the crucial problem of biology. One knew that all chemical reactions were catalyzed by enzymes and that all enzymes were proteins. But we had no idea what they looked like, how they worked. They were black boxes.
Although Perutz began his work in the 1930s, it wasn't until the 50s that he finally achieved success.
To study the structure of
When I started this work on the crystal structure of hemoglobin, the other students thought I was crazy, I was megalomaniac, to tackle a molecule with 10,000 atoms, when in fact the structure of ordinary sugar with 46 atoms hadn't been solved yet. You know, if anybody had said, it'll take you 22 years, but then you will have solved it, that would have been marvelous. In fact, I once dreamt I had solved the structure. And then I woke up, and it was so sad and disappointing that I hadn't.
Now, this little model is one of the very first that we made by means of these new methods.
Before the Braggs, the molecular structure of even the most basic materials, for example, common salt, remained a mystery. But they showed how you could fire X-rays through a crystal structure like salt. The wavelength of X-rays is the same as the distances between atoms. The regular atomic arrangement in crystals mean that the beams are deflected to produce a complex pattern of spots on a photographic plate. The position and intensity of these spots then provides the key to unlocking the structure. In Dorothy Hodgkin's case, the structure was penicillin.
Now, what she began with was something rather unpromising, this rather smudgy grey photograph with some little black dots on it. And she would simply compare each dot with her reference set of dots and mark against it how dark each particular spot was. And having measured the intensities and indexed the positions, she would then write them down in her notebook in these columns and columns and columns of figures. And that was her raw data from which she was going to use to find out exactly where in three-dimensional space each atom of the penicillin crystal was.
The work was painstakingly tedious, but the prize for success would be enormous. If scientists could understand the structure of penicillin, then there was the possibility of designing and synthesizing new, even more powerful drugs. Dorothy Hodgkin was working on penicillin during the Second World War, which gave her meticulous indexing of spots on the X-ray plates added urgency.
You've got to unravel all that. You've got to work backwards from the spots to the positions of the atoms, which is what takes this incredibly complex mathematical calculation, which indeed in Dorothy's day was entirely done with very little more in the way of assistance than an old-fashioned adding machine with a handle that you cranked on the desk. Well, then, having got all these figures and performed her calculations, she's drawn out the densities in each place very neatly. So you've got this grid of little tiny figures. If you look at this particular one here, the highest number she's got on this grid is 334. And around it, she's got 314, 321, 308, 322, all quite big, but not quite as big as that one. So she's drawn a contour line, like a peak, like a mountain peak on an Ordnance Survey map. And then a bit further out, the figures have gone down to around 200, between 190 and 200. So she's drawn another contour line there. And this is how she begins to see the structure emerging from this fog of electrons. The highest points represent the greatest density. So you've got something there. There's going to be an atom there. What she was able to go on to do was to plot out each individual level on Perspex sheets and build a model that enabled you to see it as a three-dimensional structure. The final step is to take your electron density and plot onto it exactly where the atoms are, and that's what she's done here. You can see her original contour lines behind, and on top of that, she's just drawn in a model of the penicillin molecule. These are the atoms, as you might expect to see it in a chemistry textbook. The key part of it, this point here, which is called the beta-lactam ring, which is why penicillin works. It destroys bacterial cell walls, and that's why it kills bacteria. But for a long time, some of the best chemists in the country didn't believe that this structure was part of penicillin, and Dorothy proved that it was.
Meanwhile, in Cambridge, Max Perutz was continuing with his painstaking work on the even more complex molecule of hemoglobin.
Now Max has come back the next day and stops the exposure and takes out the film to be developed.
For years, I just took X-ray pictures and measured spots, and then finally, in a primitive sort of computer, in this vector structure was calculated for me. 1949, this diagram finally came out, and I was jubilant because I thought I could see traces of parallel protein chains, and I really thought I'd solved it.
But a new research student, a young Francis Crick, had just joined Perutz's team. Crick was later to share the Nobel Prize for discovering the structure of DNA.
The first result he showed me, he was a much better mathematician than I, was that my model was fundamentally flawed. There was an enormous amount of work invested in this, and imagine my feelings when I realized that all this had been wasted.
The effort was incredible. It lasted for 20, 30 years and was rewarded by seeing what to me is simply the most beautiful molecule we have.
Well, it was tremendous. You know, I always say it was like reaching the top of a mountain after a hard climb and falling in love all at the same time.
The hemoglobin molecule, the first time it was seen, looked pretty wild. It certainly doesn't look like anything simply beautiful. Beauty resides at the tense edge, that's how I think of it, where order and disorder, symmetry and asymmetry are fighting with each other.
X-ray crystallography is still a key technique of modern science. Today, crystallographers work in much the same way as the early pioneers. But once crystals are obtained, computer processing means that structures can be revealed in hours rather than years.
By now, X-ray crystallography is pretty routine. In a half man or woman day of work with a machine costing $500,000, you can determine the structure of a small molecule. It's no sweat.
What crystallography shows you is atomic structure, while optical microscopes let you see only relatively small objects. So that still left a large middle ground that was invisible to scientists. The solution came in the 1930s when scientists began to experiment with another imaging tool, beams of electrons. At last, the middle ground could be revealed, but at first, only in 2 dimensions, because specimens had to be prepared as wafer-thin slices. That would all change with the invention of a new tool in the 1950s.
This is a millipede, what I call a mini monster sometimes. The bugs are wonderful for familiarizing people with scanning electron microscopy.
The scanning electron microscope, or SEM, allowed whole specimens to be imaged in a familiar 3-dimensional way.
To get this picture, I took 2 long strips of Velcro, put them together, pried them apart, just left one edge, and then flew along it with the electron microscope. And you can see here how tangled the mess is and why it's so hard to pull these things apart, why they make such wonderful fasteners.
Lead.
Lead, you've got lead. We'll just check for where...
Dee Brieger runs the Scanning Electron Microscope Lab at Columbia University.
We can confirm that in a minute.
A micrographic artist, she works alongside other research scientists, helping them investigate their samples.
This is the shell.
Yeah.
And you see these are like the growth rings.
A scientist will want to get inside and see the structure inside. You can't do that with a light microscope. And you can't take a picture with a light microscope that has this overall 3-dimensional quality that the SEM can give you. If I had to choose another all-time favorite picture, this one would be it. There's a serenity in this one and an impact in this one. We're seeing a radiolarian shell that's nearly invisible to the naked eye, a tiny, tiny little white dot, that houses a 1-celled animal deep inside. This is literally a glass house. It's made of silicon.
I love looking at those patterns, and they are so distinct. Sometimes I wonder if those patterns are creations of the photographer's art. The contrast is so intense, and they are so 3-dimensional. But I think they're incredible.
The human mind likes to relate the images from an invisible world that's parallel to our own world, but unseen by us, to the world we live in. And the electron microscope, the scanning electron microscope, can do that very well. It's as far as I'm concerned, its primary function. We see things the way we could see them without the microscope, and we can relate to them. We can put them in context of our own humanity. I'm pouring hundreds of little microplankton onto this prepared stub. It's got double stick tape on it, and they are sticking, and I can get off the excess by tapping them off. Under the scope now and take a look. Oh, they look pretty good. So next thing to do is to put them in the sputter coater, give them a coat of metal to make them conductive. After the samples are prepared, it's a very simple next step, and that is to place them in the sample chamber and pump most of the air out. Open up the microscope, the chamber. Now, that's the one with the worm tubes on the shell. Put that one in. That sets the stage for firing the gun, and the gun is above the sample chamber at the top of a stack of electromagnetic lenses. The electrons, they don't go straight down, they actually spiral down. When they come out of the final lens, they land on the sample below, which we can position in any number of ways, tilting and rotating. And that sets off a sequence of subatomic events. And we have multiple detectors arrayed around the sample that pick up these different events, and each one creates a different kind of image.
Although electrons provide stunningly realistic pictures, they lack one thing: color. The SEM only images in black and white.
I've just brought up on the screen the original black and white version of the mosquito wing, because I want to separate out by color the three different kinds of features that are in this image so that they'll be easily discernible to an untrained eye, and also so that they'll be more appealing. Everybody loves color. What I like to do is create a scientific picture with content that is meaningful, but I like to make it artistic in the sense of a balanced composition and balanced blacks and whites. The person in the scientist enjoys the colors as long as they're not false to the integrity of the sample. Work that requires infinite patience, that's very rewarding at the end, very rewarding.
Don Eigler is using electrons in a radical new way to actually image atoms on surfaces. And he not only looks at individual atoms, he can move them around too. To do this, he uses a scanning, tunneling microscope.
When we operate the microscope in the imaging mode, we keep the tip far enough above the surface so that when the tip comes along, it starts to pick up some electric current from this atom. The tip rides up and over that atom and then back down again on the other side. So we can image the atom, and the atom shows up as a bump. That's the trajectory of the tip that we end up measuring. To move the atom, what we do is we take the tip and put it directly over the atom that we want to move, and then lower the tip towards the atom in order to increase the attractive force between these two atoms. If we bring it to the right height, then if we then move the tip sideways, we can drag the atom with the tip to some new location, get it where we want it to go, and then pull the tip back and go back into the imaging mode. We take the electrical current, or the signal corresponding to the electrical current, and put that into the stereo system in the laboratory, and we listen to that. We provide that information for our ears. Our brains are very adept at processing both audio and visual information at the same time. Our eyes are busy seeing where we're moving the atoms, and our ears are busy listening to whether the atoms are moving in the way that we think they should be moving. The way it images is not at all like an optical microscope or even an electron microscope. Yes, they both use electrons, but an electron microscope is really much more like an optical microscope in the sense that both kinds of microscopes bend waves in order to create magnified images. An optical microscope bends light waves, an electron microscope bends electron waves. A tunneling microscope is much more like the way you could sense the shape of something by closing your eyes and using your hand to feel what the shape of something actually is.
Some people think that science and art are somehow different worlds. What we see in a painting is an artist